So I'm going to talk about the physics at the boundary of fusion plasmas, really, and specifically of what are called Tokamak plasmas. And I'll tell you what that is as we go along. This is a picture I took at the Burning Man Arts Festival in 2010. And we were burning down a giant, beautiful temple. The whole idea is you build art and then you burn it down. And we'd prefer not to do that with our fusion experiments. We'd prefer if they didn't get burnt down once a week, which is at the end of the week we burn this down. But they do take, here's a guy doing a video of it, and I'm back here taking a picture of him taking a picture, right? And so we did do pretty good diagnostics on this. You can see bits of the house burning back here. It's really quite a beautiful sight. But we prefer not to do that in our fusion plasmas. And I'm going to tell you about the challenges of not burning up our fusion plasmas. Because after all, we have 100 million degrees, 200 million degrees centigrade fusion plasmas. Those are the temperatures you need for fusion to work. We've got those, and somewhere we have a material surface. And obviously, if you bring a 200 million degrees C object in contact with a material surface, something interesting is going to happen. And that's what you call in the physicists. Okay. So in the outline, I said I would tell you something about what's needed for fusion and sort of give you the very biggest picture before we delved into thinking about the plasma surface, the boundary of the plasma. So I'm going to argue that you need three things really out of the plasma physics. There's a bunch of engineering things you need too, but there's three things you need out of the physics of these devices if you're going to eventually be able to sell electricity. The first one is that whatever this object is, it had better make electricity. It should make net energy. It should make much more energy than whatever energy it took to power it, to run it. You know, you had to turn the lights on in the control room. You had to do whatever you had to do, cool things, heat things, to get it to operate. It had better make way, way more power out than you were, for example, putting in to heat this hot plasma. So you need much more fusion power than whatever it took to get to the conditions you want, or whatever it takes to hold you in the conditions you want. So now this is volumetric. This is power density here from fusion. And the fusion reaction we're going to talk about is deuterium, which is 1 proton plus 1 neutron, colliding with tritium, which is 1 proton with plus 2 neutrons. So that's the D and the T there. And these are the volume densities of those two, the number density, number per cubic meter in SI units. This is the rate coefficient for the reaction. This is the cross-section of the reaction, which is a function of the relative velocities of the two particles coming together. And in nuclear physics, that tends to require a fair bit of energy for that to happen. This is the relative velocity of the two objects. And then you average this, that's what these bars are about, over the Maxwellian Gaussian distribution kind of the deuterons and tritons to get this reaction rate. Now, as some of you may have been through this in various classes. Actually, how many people are familiar with a reaction rate like that? Of order half, okay. So how to put this? We all like to think we understand this all perfectly and we know exactly why that is a reaction rate. But when worse comes to worse, you can look at the dimensions anyway and see if this makes sense dimensionally. So a sigma is a cross section, which means it's an area, length squared, and a velocity is a length divided by time. So let's take the time and remember that this is going to be a fusion power, so it's going to be energy per unit time. So that's where we got the time. This is a number per unit volume, so a number over length cubed. So we just got rid of all those length cubes. And now we have, again, a 1 over volume, a 1 over length cubed, and an energy, and you remember that time we had before. So we have an energy per unit volume per unit time, otherwise known as a power density. So that's a way to at least check that I'm not cheating on the equations. And in the range that we want to operate, at the temperatures that we're interested in to get fusion to really go, this sigma v, which is going to depend on the velocity of these particles and therefore their temperature, it goes about, sigma v goes about like t squared. And so there's various arguments you can make about why you want to operate where sigma v goes like t squared, but take it on faith, I guess, that it goes like t squared. It's roughly correct. And then if you're half deuterons and half tritons, let's consider this proportional thing to have a 1/4 stuck into it. So it's something like the ion density, the number density of the ions. The deuterons, say, are half of the ion density. The tritons are also half of the ion density. So this whole thing scales proportional to the density squared times the temperature squared and a bunch of other constants. So that's sort of a fact about fusion. In fact, it's true of any reaction you want to use. You're going to want to operate in the range where it goes like t squared. Now then, there's also power being lost from this fusion, and this is now going to be volumetric power density, so power per unit volume. And so we know that the energy density in a plasma is equal, well, fully ionized gas, a plasma, is equal to the electron density times their temperature, where I'm implicitly using Boltzmann's constant. You can see a little tiny Boltzmann constant there if you look very closely. Obviously, that's not what's going on. I'm writing down temperature in units of joules, if you like. So this is a temperature in energy units. So it's actually 3/2 T is going to be the average energy of a particle. I mean, it's kind of obviously, I guess, 3/2 T is the average energy of a particle in this plasma. And you know that from elementary statistical mechanics. And so the electrons have this pressure, the ions have that pressure, together they have this energy density. So I have an energy density of this plasma. Typically, it might be equivalent to, this pressure might be equivalent to, say, 20 atmospheres. Not vastly high, but pretty high for a tenuous gas, because these temperatures are hundreds of millions of degrees. So that's the energy density, and it took some power to sustain this energy density. There's going to be some loss leaving the plasma. We'd like that to be way less than the power that comes from fusion. And so we just define it. This has the units of energy density. We want power density. So we just define that ratio as this energy confinement time. It's really almost the definition of energy confinement time. It's the characteristic rate at which energy that's in this plasma turns over. It leaves with this characteristic time. But now what we'd like is the fusion power to be vastly larger than the loss power. And that way we can, plug something else into our fusion reactor rather than plug our fusion reactor into something else and have it get power from outside. We want to make power inside. So we want this to be a big number. There's a little more to it. The fusion reaction actually creates some alpha particles that are up at 3.5 MeV, and they can supply this loss power. Then you don't need anything from outside. But you do want, this number needs to be big, is the basic thing you're after. And the answer is that we've made some progress on this. Here we have this fusion product, sometimes they call it a triple product, and it's NT tau or N tau T. So this thing I've just derived for you. So here it is on the vertical axis, and these are orders of magnitude. And here is the central ion temperature. And if you want lots of gain, it's good to be at about a little above 10 kilovolts for the average ion temperature, meaning the average ion has an energy of, say, 15 or 20 kilovolts. And that means that you can get, with a given triple product, a certain amount of gain as you go up, a certain amount of extra fusion power compared to what you put in. And so when I was a young whippersnapper, a graduate student, I worked on experiments down here. This one's in Russia, but we had one in Princeton that was somewhere down here. And then right after I got my PhD, I worked on this experiment. And then I worked on the Tokamak fusion test reactor that made its way up by a couple of orders of magnitude along this chart up to the top here. And we haven't gone further because we're building this international thermonuclear experimental reactor in Cadarache, France, which will get us up to very close to reactor conditions, if not exactly ignition, where those alpha particles are doing all the work. Very high P fusion over P loss, 50 or something like that. So that's a pretty exciting place to be. And that's, I'm sorry, more like 10 for this number. And so that's a very exciting place to be, and that machine is coming together pretty well now. We had a series of directors who didn't understand European politics, and now this guy Bernard Bigot, who is in charge, is a connoisseur of European politics. I think he enjoys playing the European politics game. And he's managed to get this thing built and negotiate with companies. He's doing a very good job. I particularly like it because he followed some of my, well, he probably figured out for himself, but he did follow what turned out to have been my suggestions. So he did some great stuff. So anyway, one thing you want is this thing to make net power, and that's where we're headed. Now the other thing you need is a plasma that's stable. And in other words, it's fine if it makes net power, but first of all, it shouldn't tear itself apart in a microsecond, because it costs, $5 billion and it tears itself in a microsecond, and the next microsecond you're going to build another $5 billion machine. Doesn't sound like a good idea. So it's got to be sitting there stably, not damaging itself. And it also has to make a fair bit of energy, a fair bit of power. So here, if something this big makes 100 watts, yeah, that's pretty good. But if something the size of this complex makes 100 watts, that's not saleable. So you have to have not just net gain, but also good power density. You need for a given size thing to make a lot of power. So let's go through the same argument we went through before. So fusion power, I said, goes like this, which goes like Ni squared Ti squared, we argued before. And then let me introduce a parameter called beta. And we see a lot of this in fusion. What this guy is the pressure in the plasma, again, the electron density times the electron temperature plus the ion density times the ion temperature. So that's the pressure in the plasma. And you may not have run into this. This is a kind of a slightly advanced electromagnetism thing. But this is the energy density in the magnetic field. If you create a magnetic field of a certain size over a certain volume, the energy that it took to create that magnetic field, the 1/2 Li squared if you're a electrical engineer, that energy that went into creating it is the volume integral of B squared over 2 mu naught. So you'd like to make a lot of fusion for not too much magnetic field. So going here, N squared T squared is going to be beta squared, because I want to square this, but then I squared this thing, so I bring him over, and the magnetic permittivity isn't going to change, so I can put that into the proportional sign, and I end up with the fusion power density going like beta squared times B to the 4th. Now we turn to the engineers, we say we'd like as much B as you can muster for us, and there are some new ideas about high temperature superconductors that may be able to push this up, but there's going to be some engineering limit to what B field you can get to. And so you want a pretty high beta so that you don't need a ridiculously large machine. This is power density, and so if beta is too small and the power density is too small, I need a gigantic thing to make 100 megawatts or a gigawatt of electricity. So I want to push up this beta parameter. And so I'm going to show you results from a machine in Princeton, but it's just one of the many machines in the world that have studied this. And so this is the beta that we get to. This is in a donut, and the toroidal direction is the long way around the donut. Okay? And so we're just, in this case, counting the magnetic field here that is in the toroidal direction. So there's that parameter in percent. And this is the current that's flowing around the donut. Going around, you have an electrical current typically in these machines, and definitely in Tokamaks, there's an electrical current. This is the minor radius of the donut. So it's, whatever size it is going around. The minor radius is this radius. And this is that magnetic field. And what we predicted theoretically, and what we have found experimentally, very nicely actually, is that the beta you can get to depends pretty much linearly on this. That's the maximum beta you can get to. And if you don't put in enough power, you're here or you're here. You have some confinement time, so you put in some power, you get to some energy density, and here, and you keep going, add more power, and oops, you can't go further. And oops, you can't go further, and oops, you can't go further. Really, pretty much along a straight line dependency here. So this is pretty well understood. It's reasonably adequate for a fusion system. And so we kind of solved this second problem. We understand confinement, we can get gain, we understand stability, we're able to have it sit there. These things sat there for multiple seconds. We have experiments that have gone, I guess the very high beta ones have only gone sort of 5 or 10 seconds. But that's limited by the magnets that we have. So we kind of, have a pretty good handle on stability. Now, the guys who do confinement, do stability, could give you long lectures on how there's room for improvement and more science to be understood and all that good stuff. But I'm going to argue that it's the next topic that is the fun one. If you've succeeded in confinement and you've succeeded in stability, you're making a lot of fusion power, and you're making it for a long time, and you didn't have to put too much power in, and so you think you're happy, except for the other thing you need, which is you need this to go on for a while. You need this to run steadily. So you need the internal components of this system, the system that holds this big donut. That stuff has to last for a long time. Andrea.
Yes. You showed that the beta 6 is more or less your upper limit. Don't understand exactly.
This beta normal of 6. Oh, that's a whole theoretical calculation. And it turns out actually that this is a case where you can write some things down theoretically, and I could carry you through some of those derivations, but it turns out to depend on the details of the exact shape of the plasma and so on, and so you end up using big codes. And the big codes are really what gave us those results. Actually, when it first came out, when we first understood this relationship, experimentally, the theorists went off and they worked on it, and they came up with no answer except for their computer codes agreed with the experiment. And so we stopped torturing them, they stopped torturing, I'm an experimentalist, we stopped torturing them, they stopped torturing us, and we moved on. And actually, a thing that has happened a lot in fusion plasma physics is that where we used to do analytic calculations and try to compare them with experiment, and things were reasonable, but there were always big questions, has now been replaced with much better computation. Computers have done a good job, have obviously made a lot of progress. Not so fast actually as fusion has, but a lot of progress. We complement them. And the result is that you can do a lot of these calculations now, really, including precise details that you couldn't really with an analytic hand calculation. Okay, so the next thing that's needed for fusion is long-lived internal components. All this heat's coming out, and you have to handle it somehow. And as I said at the beginning, the middle of the plasma is at 200 million degrees centigrade, and the wall is, whatever temperature, maybe 1,000. Yes? Great. This is a great. The next slide is going to be great. Yeah. Go ahead.
So I was wondering, is there any relation between the stability and this plasma lifetime, which was the first time?
They actually have some similar scalings. They both care a lot about the current that's in the plasma. It turns out that if you make a strong current flowing around inside the plasma, that is, as you saw on the last slide. It obviously a higher current lets you get to a higher beta, and it's also true that a higher current lets you get to a longer confinement time, that tau e parameter. And essentially what's going on is that both large-scale instabilities, big motions of the whole plasma, which are what set the beta limit, when these things go, they typically lose control with finite mode numbers, with say n equals 3 or 4 to mode numbers around the tokamak. So it's something that's going this way, that way, this way, that way as you go around. And that's stabilized by connecting the inside with the outside with the magnetic field very quickly, having a very strong poloidal magnetic field that goes around the short way. and that's and I over A, it's plasma current makes a poloidal magnetic field. Plasma current going this way makes a magnetic field that way, and that drags the magnetic field lines around. And so that current stabilizes the large-scale stuff, which is this. And it also turns out it stabilizes very small-scale stuff. And it's the small-scale stuff that gives rise to the turbulent loss of energy, to the tau e, to the shortening of tau e. And it turns out, and it's sort of reasonable actually, that both on the macro scale and on the micro scale, this plasma current is a very good thing. But they're very different. You can run a machine which will sit stably. So these experiments sat stably for say a second, and the energy confinement time was maybe 50 milliseconds. So 20 energy confinement times. So it's a different piece of physics. Okay? So, long-lived internal components. So the current state of our internal components can be summarized with the original picture I showed you. If we were to take what we currently understand about plasma-facing components and put them inside of a fusion reactor, they wouldn't last too long. We clearly have to get a better understanding about how the heat flux connects to the walls and then how to handle that. I would argue, and I have argued, that this is kind of where almost literally the rubber hits the road for fusion. We've succeeded enough that we know we can make gigawatts of power in a fusion plasma, but we don't really know how to handle it. And that's it's a major scientific frontier, and it's one of the frontiers that's being, it's the Differ experiment, the Differ facility, the Magnum PSI experiment in Eindhoven is right at the forefront of doing this kind of research. So you guys are right at the forefront. So there has been a tremendous amount of advancement in our understanding of this problem in about the last 8 years. There were papers published in 2011, 2012 that just opened up this the frontier of understanding of this, changed essentially everything we thought we knew about it. And so you're going to now be taken from 2011, let's say, the year before the 2012 papers, up to the present in the course of this lecture with a little luck. Particularly since we seem to have a lot of time, so we can answer questions, we can have fun. Okay, so the theme of this lecture is all this bit. So what we're going to find is that the heat flux, if you don't do anything about it, that would just come out of the plasma, is really high. And it's because this remarkable result, the scrape-off layer, and I'll tell you what that is, but it's the region where this heat comes out of the plasma and goes and hits the surface, this where we're scraping off the edge of the plasma. So that scrape-off layer width doesn't get bigger as the system gets bigger. It had always been assumed, like from my childhood until when I was 20 years old 10 years ago, that it was just assumed that this would be true. Everybody was designing reactors and projecting to the future. They just assumed this. And I'll show you why. It's a very reasonable thing to assume, actually. It's just wrong. And then they'll tell you about the fact that we need to detach the plasma. We need to come up with ways to separate the plasma from the wall. And I'll explain why that's turned out to be difficult and and how we understand it much better now. Or at least we're at the boundary of understanding it much better. So, unmitigated heat flux is high because the scrape-off layer width doesn't vary with the machine size. I make a twice bigger machine. Turns out the bloody scrape-off width is about the same size. Some of the guys doing reactor designs in Europe are a little bit committed to this old-fashioned thinking. And so every time they have a machine that's bigger and it doesn't seem like it's going to work, they say, well, let's make it twice bigger. And then when that doesn't work, they say another factor of 2's got to do it. So it turns out this is not going to do because the scrape-off layer width doesn't vary with the system size. You're not supposed to report that to the guys who do these reactor designs in Europe. So let's talk about what's going on inside of these systems and then talk about what's going on right at the edge. So what have I got here? First of all, you have to recognize that while this is a two-dimensional picture, it's a projection on a plane, and this goes around in a circle, right? This is a torus. This is a cross-section of a torus. What it is, we'll talk about in a moment, but it's a cross-section of a torus. Now, what's going on here is that there's a magnetic field in the middle that goes around and comes back again. And if you all did your homework, which I sent out to you from a fine textbook whose author I'm too shy to mention, you know that the charged particles spiral along magnetic fields at zeroth order. They spiral along magnetic fields. They also do this drifting stuff we talk that's later in the lecture notes, later in that chapter. But they basically spiral along magnetic fields. So the trick in a tokamak is that the magnetic field goes around the donut. I'll try not to put a laser in your faces, and comes back and goes around and comes back. And actually, if it crosses here on one passing, on the next passing it might cross there, and then there, and then there, and here, and it will eventually trace out what gets called a magnetic surface. So here's one magnetic surface, here's another magnetic surface, and a particle that starts here goes around the donut many times, but always stays on that same magnetic surface if there's no turbulence. And if these drifts aren't too important that I was telling you about. Actually, the drifts are kind of interesting. What they do is B cross grad B is the direction of the drift. So B is basically around the donut. Grad B is facing inwards. Magnetic field is higher on the inside than the outside. The reason it's higher on the inside than the outside is that toroidally directed magnetic field is formed by a current over here. And we know that the field from a current that's going vertically this way and coming around the back and coming up again, that the current, this current makes a magnetic field that falls off like 1 over r because integral of B dot dl is related by Ampere's law to the current through the middle, and the integral dl is 2 pi r. So 2 pi r is bigger here, smaller there, so the magnetic field is bigger here, and the magnetic field is smaller there. Anyway, so the particles go around the donut, they trace their way around. If they're drifting downwards, B cross grad B is downwards, you say, oh my God, this particle's going to leave. But mainly he's going around the donut, and up here you say, oh, downwards, oh, he's coming in. And he goes downwards, oh, he's going to leave. Upwards, he's coming in. It ends up the orbits close on themselves very beautifully. So the particle trajectories are well confined on the inside here. Okay, but eventually, by turbulence, or even just those drifts, particles might just cross this magnetic surface. This is a separatrix. So this is the magnetic surface that defines the edge of the plasma. And what's going on is there's a magnetic coil down here that's carrying current in the same direction as the current that's inside the plasma. So this is making magnetic field, let's say, that goes upwards. So this guy is making magnetic field that goes upwards. Over here, his field is going inwards, but his field is going outwards, so there's a null point. The magnetic field from these two currents goes to 0 here, and what happens is that the field lines that were going around this guy get pulled up and go around and go back down again and go out here, but there's material surfaces here. So what we've got is a separatrix in the magnetic geometry. We've got an X point here with 0 poloidal magnetic field. These two guys cancel, and then magnetic fields that come around here. You can just calculate this on a computer if you like to see what that trajectory looks like. Okay, so now a guy used to be happily on these field lines, tapping his toe, saying up is in, up is out, up is in, up is out, or whatever, and feeling good about it. But now he's crossed this last closed flux surface, and he says, holy shit, I'm on my way to hit some material surface. This is a bummer. Okay, so once you've crossed that surface, the game is now different. And the question is, what's life like for a particle crossing that surface? What do things look like in this scrape-off layer? That's what this is. This is the scrape-off layer. Probably even says it somewhere on this diagram. No, doesn't seem to. Well, this is the scrape-off layer. So, particles, meanwhile, have gotten cold down here. This magnetic field line is in touch with material surface out here, and so he's cold. He's, well, he's not quite room temperature, but he's pretty cold because all his heat's being drained out along the magnetic field lines. And so this is a collisional plasma. You calculated again in the homeworks that the collision rate goes like 1 over v cubed. So a low energy particle has a lot of collisions. So low energy particles are diffusing by collisions actually along these field lines. Inside here, they're pretty collisionless. They're making these trajectories where up, let's say down is out, down is in, they're canceling, they're making these nice trajectories. But here, they're flowing along the magnetic field lines, but they're being impeded by collisions. They're going back and forth due to collisions. And that's what these arrows are about. Okay, so what is the characteristic time for a guy to leave this plasma? That's going to be, if you're familiar with the diffusion equation, 2 times d times tau is equal to a length squared from the diffusion equation. People familiar with this at all? You've run into the heat equation, the diffusion equation? I won't jump, I'll close my eyes and a bunch of you raise your hands. It's hard to tell with your eyes closed. But the diffusion equation, I can't, oh yeah, there's a board here. I don't know. The diffusion equation is basically d by dt equals d by dx of d by dx of density, let's say, for example, dn dt. So you can see that there's a time here, and there's 2 lengths here, and there's a d up top. So a d times a time is going to be equal to some sort of a length squared. And the factor of 2 is a homework problem. And there's another example of me doing physics by dimensional analysis. So that's the equation of diffusion of particles. So the parallel time it takes these guys to get out is something like the length that they have to go squared divided by 2 times some diffusion coefficient that's set by collisions. Okay, now then, what about cross-field diffusion? How far do they move in this blue direction? This is supposed to be bluish. How far do they move in the blue direction during this parallel loss time? Well, the perpendicular direction, L squared, goes like now the perpendicular diffusion coefficient times that tau parallel. And the tau parallel is L squared over 2 chi. This is a thermal diffusivity, but it could be a particle diffusivity if you like. And so that's down here. This is on the top. The 2's cancel. Let's see, the tau had a 2 in the denominator, and this guy had a 2 in the numerator, so they canceled. So the perpendicular diffusion is equal to the parallel diffusion times the ratio of the perpendicular diffusivity to the parallel diffusivity. Now, generally, this is much smaller than that. Moving along the field lines is the easy way to go. But you notice that this parallel connection length it's going to be some distance along this field line, say from over here down to there. That's going to be the parallel connection length. And it's really going to go around the torus to get to making the connection. But the distance around the torus is set by the system size. So it's very reasonable to think that if these things aren't doing anything too drastic, if they aren't changing with the system size, and this is presumed to be collisional, and you saw some stuff on collisions in the homeworks, and this one is supposed to be turbulent, say Bohm scaling it's called. Neither of these, where that temperature is in energy units, neither of these have size scaling in them. So you expect then this thing to scale linearly with system size. There's some parallel diffusion, it's fighting perpendicular diffusion. If the parallel diffusion has to go 5 times longer, that gives time for the perpendicular diffusion to go 5 times further. A little funny story about Bohm is that you could write down, just from dimensional analysis, that T over EB has the same dimensions, has length squared over time dimensions like diffusion. And you can scratch your head and say, I wonder whether that goes on in a plasma. And it turns out that in some very cold plasmas, that is about right. And it turns out that it has a coefficient like 16. And Bohm, who was an early pioneer in quantum mechanics and a flaming communist, came up with this idea during the Manhattan Project and wrote in his notes that he had a derivation of this factor of 1/16, but was fired from Princeton because he was a flaming communist and a very interesting guy, actually, and very smart, came up with some really interesting interpretations of quantum mechanics. And he never got a chance to write down his derivation of that factor of 16, and people spent time trying to figure out, experimentally and theoretically, why that would be true. But it's actually, in very, very turbulent plasmas, this is about right. And these edges can be very turbulent. And so, but anyway, everybody reasonably thought, up until about 10 years ago, that lambda perp scales linearly with system size. So maybe when we build a bigger machine, it'll get longer. And we had bigger machines and smaller machines, but we didn't have detailed measurements yet. Okay. So now we're going to do a different calculation to get us ready for seeing why what everybody in the field believed until 8 or 10 years ago turns out to be wrong. So let's consider a different thing. Let's consider one of these guys inside the plasma circulating around, and let's figure out how long it takes him to go some distance around here. So let's go ahead and do that. So that's going to be some kind of parallel length to get from here to there, and divided by some sort of, say, the thermal ion velocity. It's going to give us a time. Length over time divided into length. So the parallel length, let's say that it's some multiplier on the minor radius, so it's some distance around here, if we go all the way around. And so that's going to be A, but in an ellipse, that distance there's a 2 pi, of course, that I'm ignoring, but that distance gets extended by about 1 plus kappa squared over 2, where kappa is the ratio of the height to the width of this thing. So you have a very vertically elongated system. There's a longer distance to go to get around. So that's the distance in the poloidal plane here. But the toroidal field is much bigger than the poloidal field. Poloidal's this way. Toroidal, as I've said about 16 times, is this way. So the toroidal field is much bigger than the poloidal field. So if I'm following the field line, if I go an inch, make that a centimeter, in the poloidal direction, then I might have gone 10 centimeters in the toroidal direction along the field. The field is really at a fairly slanting angle. So if this is 10 times that, then the parallel length along the field is 10 times the length in the poloidal plane. Again, a small distance down here, driven by the poloidal field, well, I got a much bigger distance in the toroidal direction because the toroidal magnetic field is much larger. So my tau parallel is the distance in the poloidal direction times bt over bp divided by this v thermal I. So that's my tau parallel. But now, let's not ask the question about diffusion. Let's stick with classical physics. So there's a perpendicular drift for ions that happens, as I was talking before. Let's say the b cross grad b drift is downwards. So the guy starts here and he drifts downwards. So while he's going around, he's got a downwards drift on the top. The downwards drift is in, mind you. But let's just consider what's the net distance, or what's the gross distance, say, on 1/2 of the torus, or what have you. How far does he drift off of field lines? So this is the drift equation that we worked out, and this was the final answer in that section of Goldston and Rutherford. And the gradient of b goes like 1 over r, so the gradient of b is just b over b, the original b divided by r, with some minus signs we'll ignore. Yeah, I took MHD physics with Marshall Rosenbluth, who was the most wonderful teacher in the world, but he sort of assumed you knew the answer before you started the problem, which was a little bit kind of challenging. And one of the students got up. She became a very famous astrophysicist since then. But one of the students got up and she said, "I'm going to solve this MHD equation, but to make it easier, I'm going to set pi equals e equals c equals 1." And Marshall said, "You got it now, Ellen." So I'm not going to do that, but I do occasionally try to ignore some minus signs. So anyway, here we are, and we have 2 b's on the top, 1 b on the bottom. So we've just got a B, and the gradient turned into a 1 over R. And so Ti is something like mv thermal I over 2, mv thermal I squared over 2. You multiply by 2, and here we are. And so this is the drift speed. So during this time, we're drifting. Before we had parallel diffusion, and we had perpendicular diffusion, and everybody thought that was fine. Now we're doing parallel motion and perpendicular motion. And it's going to turn out to be a little more challenging when we get done. So the perpendicular drift times tau parallel, v drift times tau parallel. Here's the v drift in blue, and here's tau parallel in this sort of greenish, slightly vomitous yellow. And I think I carried everything down. And so lots of things will cancel. Let's see, one of these v thermals will cancel, and this bt will cancel. And we have an A here and an R there, so there's the A over R. And what we've got left is this geometrical factor, and we've got an M over EB, M over EB, or EB over M here, and one V thermal. And you all remember this from the homework, that's what's called the Larmor Radius. That's the gyro radius around the magnetic field. But I canceled the BTs, and instead what I have left is a BP, so the poloidal direction of the magnetic field this way. And so this is the Larmor radius in the poloidal magnetic field. And this is the minor radius compared to the major radius, and this is something to do with the elongation. And what I've just told you is, holy shit, this drift times this tau also doesn't depend on the machine size. Now, the first news from that is, oh goody, that's a really good thing, because it means that particles that are inside here are doing that vertical drift and then more vertical drift and so on, and cancel, those drifts cancel. But for a big machine, make this now not a machine with, say, 1 meter major radius, but 6 meters major radius, the size of the drift is the same, but now it's 6 times smaller compared to the machine size. So the particles are better confined. The machine got bigger, but the orbits stayed the same, or maybe even got smaller if the magnetic field got bigger. And so they're really nicely confined. And so this is why you can have a party and say that ITER will make all this power. Partly because the particles are so well confined along the magnetic field line. Until you say, well, what about the edge? You say, well, what about the edge? Well, what about the edge is that really good magnetic confinement in here means really good magnetic confinement out here, and you're screwed. This is a very, very narrow region. If a particle drifts out into that region, if it isn't tremendously turbulent to move him out very quickly, he's going to follow this drift stuff. He's going to come down and he's going to drift by this amount, and then he's just going to leave. And he's going to leave having not gone very far. So it's not going to be large compared to the system. It's not going to get bigger with the system size. So this is a tau parallel. This could have been, once I'm out here, he only gets one go at it, right? He's out here, he's drifting downwards. But during that time that the particles are moving downwards out here, flowing downwards out here, they're drifting some distance, but that distance did not get bigger when the machine got bigger. And so all of the assumptions of 30, 40, 50 years of thinking about the scrape-off layer and saying, well, we can put that off, we don't have to worry about it, now has to face the fact that the scrape-off layer, and I'll show you a more careful derivation in a moment, is very, very thin, just at the time when the power is getting very, very high, which takes us back to that picture from Burning Man. So, does not scale with the system size. So now then, let's go through a little bit more formally that derivation of this scrape-off width. So what's happening is particles are drifting downwards. I've chosen the downwards direction here. They're drifting downwards in, but this is from a very cold scrape-off layer into the main plasma. And now we have hot ions drifting out, and some of them will follow the field lines back up and make one of those trajectories like we saw before that is confined, and okay, so it went through a region that was that is open field lines, but that particular particle didn't notice it, it just did this. Okay, so that's fine. That's what's going on the inside, right? Downwards drift and so on. But some of these guys are going to just go out and hit the diverter. They're going to hit this material surface here. It's called a diverter target down here. And during that time, they're not going to get a lot of time to drift. So let's do that. So the vertical gradient curvature drifts cross the plasma edge. Parallel flows connect the bottom to the top, just like would happen in the core. That's called the Fierschluter flow, if you like German, Schluter. But half of the parallel flow from here goes down into the verter, and the other half goes up. I like to say, and this doesn't get me that many laughs in Germany, I wish it did, that Fiersch goes this way and Schluter goes that way. I don't know. What can you say? But half of the parallel flow goes the wrong way. And the time scale for the parallel plasma loss, let's say the particles have to accelerate up. It's actually now a fluid flowing down here because it's collisional, as I told you. But since there's zero pressure down here, we're just really hitting a material surface, it sort of speeds up to the sound speed, just like if you try to blow a gas through an open hole, it sort of speeds up to the sound speed, which is sort of like the thermal velocity. So there's the same kind of tau parallel. This is like a V thermal ion there. And then the cross-field drifts set the scrape-off layer width. They drift down here. Electrons sort of have to come out to meet them, but the ions are stiff from their drifts. And so it's this same story. It's just the story I showed you before. You get this extra factor of 2 from that, if you like. But this is the story. This is how it comes out. And so, and again, no explicit size scaling in lambda perp. It's the same physics. So I'm far too humble to name the guy who wrote this paper, but he was roundly condemned, as he is frequently because he always comes up with bad news, until they saw the data. And then they condemned me even worse, because like not only had I come up with bad news, but I was actually kind of new into this part of the field, and it turned out to be correct. This is a worse sin. So here is data over, it's only in one order of magnitude. It's nice to have more orders of magnitude, but it's accurate to about 25%, this model. And here are very high field machines, and here are very low field machines. And so this poloidal gyro radius is way smaller because of the higher magnetic fields here, and the lower magnetic fields there makes these guys much bigger. And these are what are called type 1 LME modes. These are the very best confinement. This H mode means high confinement mode. They're modes with actually rather low turbulence at the edge. And that's probably why this classical result, this very classical simple calculation, proved to be right. And again, it scales with intensive variables. That means a variable that depends on local parameters, not something that depends on how big the steam engine is. It depends on how hot the steam is, if you go back to the origins of thermodynamics, right? So it's an intensive variable. And so it's uniformly bad news. This is a challenge. And furthermore, the individual scalings fit this heuristic drift model rather well. So this was the experimental data with different quantities of machines. These are some machines with very low aspect ratio. So they were supposed to be which is R over A, major radius divided by minor radius of the donut. So these were machines with extremely, let's say, large minor radius, almost as big as the major radius, really fat donuts, more like an apple than a donut. Actually, an interesting story is that one of those machines I worked on way at the beginning, right after I finished my thesis, was the Princeton large torus, this big donut, about 1.5 meters in major radius, probably 40 centimeters in minor radius. But it was so low energy back in the 1970s that it had actually less energy in it than the Dunkin' donut. But that's not true anymore. That's not true anymore. Anyway, but the projections for ITER and demo, any demo, any demonstration power reactor that has a high magnetic field, is that this scrape-off width is like 1 millimeter. And you can see this. Here is the most important scaling parameter. This is the model, and it says there is no scaling with radius, with size. The scaling is just supposed to be dead zero. And the experiment is not inconsistent with dead zero. And there's way more data, I should say, in this data set than in the other data sets. So it's pretty much nailed it. And they did some one-to-one machine scalings too between the Azdex upgrade Tokamak in Munich, in Garching near Munich, and the Joint European Torus near Oxford. About a factor of 2 different size machines. And there was just no variation. So this really nailed it. And now, well, I guess they hated me more, but they listened to me more too. because now we had to deal with this, because this was experimentally confirmed as well as a theory. So we had a much better understanding of what goes on here. So that was the first third of the lecture. The unmitigated heat flux is going to be high because the scrape-off width doesn't scale with the system size. If we have a little time, if we end up finishing early, I can give you some more details about this. But basically, as you can imagine, if all that heat is within 1 millimeter of the surface and it's coming down, it is one hell of a plasma torch. It's, the field lines spread out some on their way down, and we could, if we wanted, talk about that. But they don't spread out that much. And so, maybe it's a centimeter where it strikes. So it strikes on a centimeter down here, all the way around the torus. And if you just do the numbers for a demonstration power reactor, it's maybe 120 megawatts per meter squared of heat flux. And there just isn't a material that can, in steady state, take 125 megawatts per meter squared. You can, in principle, carry as much heat as you want if you have a material, a solid surface that is very thin, and behind it you have a coolant. There's going to be a temperature gradient across that surface, back to the diffusion equation. Heat has to diffuse through it, and if it's very, very thin, there doesn't have to be too much of a temperature gradient to carry a lot of heat. So you have cool down here, some water flowing by, or some helium, or various kinds of coolants you could have. Those are the two main ones we think about for fusion. But if you go to 120 megawatts per meter squared, it has to be insanely thin, and you tap on it with your fingernail and it breaks. And there's going to be stuff going on here that makes tapping on it with your fingernail look like nothing. So you just can't. There's no practical solution to handling in steady state that much power. You could handle it evaporatively. You could evaporate away all that metal. Well, but you only had a fraction of a millimeter of it to begin with. And so you're to use the technical expression, you're in deep shit. So now then, what we need to do is find some way to keep the plasma from bringing 120 megawatts per meter squared onto those surfaces. And that's sort of where the field has moved. The first understanding was, is this scrape-off layer really that thin? Do we have to believe Goldston again? I actually had some earlier stuff I did that showed the confinement was tough, and they hated me for that. Then they made me director of a big lab, I don't know. But anyway, then we came up with this thing, and this guy Thomas Eich did really beautiful measurements on SX and jet that confirmed this. But so now the question is, it's clear that this heat flux is going to be very high. How do we deal with it? We need to detach the plasma from the material surface. We need to back it away. We need to come up with some way from the physics, because the engineers just said, drop dead. We're not handling 120 megawatts per meter squared. Go away. So the physicists had to go away and solve the problem, was really their message to us, to be fair. So go away and solve the problem. So we thought about just going away, but no, we decided to solve the problem. So we need to detach the plasma from the target. And it turns out that this turns out to be a problem. Because the scrape-off width is so thin, it turns out there's no volume. There's very little volume to do this detachment in. You've got to take away the heat in this very thin scrape-off layer. Before we thought the scrape-off layer was big. Well, maybe you could take the heat away in this big volume somehow. But now you have this tiny little scrape-off layer. So now we need to understand that physics. We need to understand this detachment physics. So that was kind of the next big challenge. And it's difficult because of this same problem. There's sort of a root cause here. Okay, so, boy, that did not come out too well. Well, you can barely see there's grid lines here somewhere. This is kind of a little bleached. If you can get a plasma below 1 eV, okay, so this is a hydrogen plasma below 1 eV. This is the reaction rate, that's sigma V, that we talked about. So this is the reaction rate for ionizing the plasma. And hydrogen really doesn't ionize too well around below about 1 eV. Fluorescent lights, if these are real fluorescent lights, I don't know if they're LEDs, but fluorescent lights run about 1 eV, because below 1 eV you don't make any plasma anymore. But what happens below 1 eV is the plasma recombines. The ions find the electrons, and they recombine into neutral hydrogen. And neutral hydrogen, bless the Lord, is not confined by a magnetic field. So if I can take this incredibly hot plasma and turn it into neutral hydrogen, and in the process make a whole lot of photons, because the recombination process dumps electrons into high orbitals in the hydrogen, and then they have to jump down, the electrons have to jump down, and they make line radiation. First they make sort of continuum at the very highest, where all the levels are very close to each other, and then they make line radiation as they come down. And maybe I'll introduce a little bit of some impurity. I'll introduce a little nitrogen or neon or something. That'll radiate away the heat, and that'll go smoothly everywhere. And so the fact that I had this 1 millimeter scrape off with won't matter, because I've radiated everything away, or I've turned it into neutral hydrogen that isn't magnetically confined. And now I've got a good story. I've got a good story. I've got a good fusion reactor. But I have to get the temperature below about 1 EV, so that the ionization gets beat out by the recombination. The plasma just goes away. So that's what I want to do. And it turns out to be really, really, really good news to do this. So this is from a machine in the US, the CMOD. This is this ASDEX upgrade in Germany. And what we have here is the pressure at the target, at the diverter target, divided by the upstream pressure. So there's some NETE that you can measure with actually laser Thompson scattering. Maybe I'll say what that is, because it's kind of a cool thing. You're interested in knowing the temperature of the electrons in these plasmas for all kinds of reasons. The radiation depends on the temperature. This physics depends on the temperature. So you've got electrons that are free moving, spiraling around and moving with some Maxwellian distribution. If you scatter photons off of them, boom, in comes a photon. It scatters off the electrons. It's Thomson scattering. It's energies where the energies of everything is below 511 kilovolts, so you don't have to worry about relativistic effects. So you're not causing the electron to jitter by, half an MeV or something crazy. It's not Compton scattering, which happens at higher energies. So it's a much lower energy event. Essentially, you're just making the electron wiggle in the electric field of the laser, and then that's just re-radiating. Well, if the electron is going away from you, so you excite it with a laser, you move it back and forth with a laser, and then if you look at it from an angle, let's see, how are we going to do this? Laser go horizontal, I'm going to look from below, let's say. So I've made insofar as the electron is moving back and forth here, that's one thing that's going to make it re-radiate, but if it's moving vertically away from me, it'll be red-shifted. And if it's moving vertically towards me, the light that it radiates will be blue-shifted. It'll be the original energy. The thing is jittering in the original energy, but the photons that it puts out from the point of view of the detector are red or blue-shifted. And by measuring that, and we've gotten really good measurements now of the light that comes off the scattering. It's, I don't know, 10 to the minus 15 probably the light that's put in. So there's a little trick to not be completely blinded by the original laser lines scattering around. But now we have very nice microchannel plate detectors that can measure all different angles at one time and all different energies at one time. It's pretty cool. So we can measure this from the Thomson scattering, it's called. Anyway, so the upstream pressure, in this case, it probably says the units somewhere, but looks like I probably snipped off the units. This might be more or less in atmospheres. I don't know what units they've got them in. But here's the pressure, and what you can see as you go down in temperature, the upstream, the pressure when the target plate is at very low temperatures can drop by a factor of 100. And this is true on ASDEX upgrade also, though their data is a little less uniform. So for a given upstream pressure, if you can get the target temperature to drop from 10 eV, which was already a challenge to get to 10 eV, because the upstream temperature to carry all this heat down is pretty high, it might be 150 eV. But if you can get the target down below 10 eV, down to 1 eV, the pressure drops by about a factor of 100. See, that's like a factor of 100 here. So this is really good news. If I can cool the target plate, I get there. Then the heat flux that comes there, which is essentially the thermal velocity carrying the energy density. That's what a heat flux is convectively anyway, and it's the dominant effect. So I've got a T to the 1/2, which is the flow of the stuff, and I've got and then I've got the pressure. So where this went down by a factor of 100, when I went down by a factor of 10 in T, carrying this pressure onto the target got slower by, say, a factor of 3. And so the heat flux went down by a factor of 300. So now we're talking turkey. 120 was too much, but divide by 300, now we're in business. Now we have a solution to this problem if we can force the target temperature down to these low temperatures. And that's this idea of detachment. Also, when you got down to those low temperatures, you maybe remember from the previous slide, you're recombining. And so the plasma doesn't even get there. So this is really good news. And interestingly, what happens is that as you raise the density upstream, and I'll give you the derivation of why this is true, and I'll even show why it has this sort of square root dependence on power. As the density goes up, you get to a certain place, and all of a sudden this recombination stuff just takes off. And a little bit more density, boom, you're down to where you want to be. So if you can get down to sort of 10 or 15 EV, you've done the business. Because now it starts into the recombination, it just turns itself off. So this is also good news. This is from a machine in San Diego. I recommend the weather there. And the physics is fun too. Okay, so now then, our goal is, pardon?
Yeah, I have a question.
Absolutely.
Yes. Well, 2 slides ago already.
Oh, you had the thing up for all that time.
Yes. So this
Sorry.
is trading. Oh, sorry, one.
Further back?
Yes.
3 slides ago.
No, so,
This one?
yes, this one.
Okay,
So,
very good.
So this scaling, if you cool down the target temperature,
Mm-hmm.
then you have a pressure drop by a factor of 100. But is that just an empirical scaling, or is that also?
There are some theoretical calculations, and this was a very old calculation, self-Ewald model, that is for uniform plasma. It's not a very satisfactory, as you can see. Actually, it's not too bad, but it's not a good model. Let's see. There are modeling. We have these codes that allow us to study this physics with some reasonable assumptions. Let me say that when I told you that the MHD codes really do a beautiful job of doing stability, and I maybe didn't say this, I hopefully said it a little more weakly, that the understanding of confinement, we have codes that do these turbulent calculations, and now we're sort of arguing about factors of 2. I mean, when I started, we were arguing factors of 100. Now the theory and the experiment matches, in many cases, even much better than a factor of 2, but they're sort of outliers. In this business, the code calculations, if you can get a factor of 5 kind of agreement, it's pretty good. It's usually not off by, I mean, Marco can maybe correct me, but it's probably not off by a factor of 10 or 20, the theoretical calculations, but they are actually very complex. Lots of atomic physics is required in this because of the radiation losses and so on. So I could not claim that we have a good theoretical understanding of that. What I am going to claim is we have a pretty good theoretical understanding of what it takes to get here. And it appears experimentally that once you're here, and this also comes out of the codes, more or less, not in beautiful agreement, but more or less, once you get here, you kind of drop over a cliff. And so actually it's a good question because it does highlight that the interesting problem, fortunately, the interesting problem is how do you get down here from a much higher upstream temperature. See, here was at lower densities, the target temperature was like 40 EV in these cases, right? And that's hopeless. You're just going to take this heat flux right on the nose. You didn't lose any energy. You got basically the upstream temperature. All the power shows up. But down here, you're in good shape. But in fact, this part, getting down here from the higher upstream temperature, is something we do understand pretty well. So this is a business that has moved much more to quality, detailed understanding, big codes that match experiments well, but we ain't there yet. There's still plenty to do, and this is an area where there is especially plenty to do. Okay? Good. Okay, so how does heat diffusion scale? Okay, so you all not only did the homework out of Goldston and Rutherford, but memorized the result. It's impressive. And you wrote it on the slide. It was good work. So the collision frequency is this formula. And let's see if we can do a little physics with this formula anyway that we can understand. And so actually, you know, I'm joking about the homeworks. If you had read that, insofar as you read and understood and did that, you've got the basis for what I'm assuming. Like I assume those things about the drifts, and I'm going to assume something about these collisions. But the argument from here doesn't depend on those derivations. But it's interesting to have a little physical understanding. So the collision frequency, which is 1 over the mean time between collisions of electrons with ions, is given by this formula. And you might ask, log lambda in the derivation shows that it has to do with small angle scatters building up and actually being much more effective than single large angle scatters, or there's sort of 20 times more effect, 16 times more effect from small angle scatters than large angle scatters. And all this other stuff is sort of going to be something, you know, the number of scatterers is going to come in clearly, and what their charge is going to come in because it's a Coulomb scattering. And, you know, the mass of the electron might come in somewhere. But the interesting part is this V cubed. So why is this 1 over V cubed? Well, we know that the potential well around a positive charge has a 1 over R energy dependence, right? That's the depth of the well goes like 1 over R. So if I choose an energy, let's choose 50 eV, there's going to be some radius that's going to give it a good hard deflection. If it's coming in with an impact angle at some radius, it's going to give it a good hard deflection. For 100 eV, I'm going to have to go to half that radius. And for 25 eV, I'm going to go to twice that radius. Okay? So the radius of the scatterer goes like 1 over energy. High energy is small. The area of the scatterer is going to go like that squared. So the area of the scatter, because it's the circle. When you study collision physics, you can, in the simplest approximation, think of the target as a dinner plate, and the guy comes by and he either hits the dinner plate or he doesn't in hard angle scattering. But in this case, if you want a 90-degree scatter, higher energy guys have 1 over energy squared smaller targets. So you say, ha, Goldston's lying again. That would be a 1 over V to the 4th. The cross section should be a 1 over energy squared, 1 over T squared. But the collision frequency is 1 over velocity cubed. So where's that other velocity coming from? Where that's coming from is you got all these dinner plates, and they're smaller when the energy is larger, but you find them V times faster. Because if you're going at velocity V per unit time, you hit 6 dinner plates. But if you're going at half that velocity, you only hit 3 dinner plates. So there's a V in the numerator here. You hit them more with proportional to V. So the scattering frequency, the rate at which you hit them, is the cross section, which has a V to the 4th in here, actually you can even go back to my old sigma V, right? Rate coefficient. So there is the cross section has a 1 over V to the 4th, but you multiply it by V to get the rate, and lo and behold, you have a 1 over V cubed. Okay, so that's the scaling of the collision frequency. So a parallel electron thermal diffusivity is going to be a length squared over 2 times a tau, which is why I put the tau there. And so that's going to be, the length is going to be something like the thermal electron velocity squared, length squared, times the tau e squared with this. Now, this is a pretty big squiggle because I'm averaging over a Maxwellian, and so this tau has, a tau squared has in it this V to the 6th, you know. So I'm winging it on doing that averaging over a Maxwellian. And so this is just giving you the basic scaling, but not giving you the factors in front. Because when you averaged with that in the averaging, it's a big deal. Okay, and that gives you a coefficient that is important. But we go ahead and do that. But actually, before we do that, let's say we go ahead and do that, make this approximation. We divide by the taus. We're on top of this. And now we get that the thermal diffusivity has a V squared, a V thermal E squared. And now if I take this to a thermal distribution, and I want tau, not 1 over tau, I have a V to the 5th. And by the way, I got a 1 over density. The ion density is going to be proportional to the electron density, and this is a proportionality. So I've got a V to the 5th over n is the thermal diffusivity. That's where I got to. And so that's like a T to the 5 halves divided by n. So this is, unlike many things in nature, very like almost anything else in nature, a much, much better thermal conductor when it's hotter. Really, 5 halves faster thermal conduction. And so the thermal diffusivity is going to be some constant, all this gub here, some constant times TE to the 5 halves over NE. And now we're going to get a cool result. So the parallel heat flux, if you look at this thing, what this is the divergence, the dN dt is the divergence of the particle flux. So the particle flux is d grad n. So the heat flux is going to be the thermal diffusivity, but the thermal diffusivity, which is just the length squared over time object, to get conductivity, to get parallel heat flux, needs this to be an energy density. You can maybe imagine you need that if I'm going to move things around with length squared over time kind of diffusion, then I need the thing to be energy if I want what's coming down here to be power or power density. But in general, you have to multiply thermal diffusivities by a density to get a thermal conductivity. So you do that, and you're here, and lo and behold, the density dropped out. And the reason is essentially that the number of carriers of this heat goes like the density. That's the number density of the carriers, all these electrons that are carrying heat back and forth. But their collision frequency goes with n. The collision frequency goes with n, and so their degree to which they're being stopped gets canceled by the number that they are. So it just comes out of the equation. It's a little bit of a hand waver, more even than I usually do. But now what's interesting is, oops, we're here. We can take this over to this side, take out a 2/7, and we have that Q parallel is some constants times grad parallel along the magnetic field of the electron temperature to the 2/7 power. So if in the simplified limit that this is a constant along the magnetic field, then this is just a first derivative, and we can then simply say that this is like a 1 over L parallel, because this is a constant. So the gradient is constant, and so we just integrate it, and we get an L parallel here. So we get really a 1 over L parallel, an L parallel when we do the integral. So we get 7 halves L parallel Q parallel over this kappa naught guy to the 2/7, because we want to get back to this T. That's the upstream temperature. And we just know it. It's really simple. And it actually turns out to be experimentally validated and really well understood. That the electron temperature up at the edge of the plasma is connected to the length along the field line, to the amount of heat flux, power density of heat, to the 2/7 power. And so this doesn't vary too much. Even as you go to bigger machines with a larger L parallel and perhaps a higher Q parallel, because of lots of power, you're still taking it to 1 over 3.5 power, right? So TE separatrix in current experiments might be 100 eV, 50 eV, 120 eV, but in ITER and in a reactor might be 200 eV. So a huge jump to a bigger machine, and like a factor of 2 jump in this TE separatrix. So I think we got to quarter of. Yes, we did, exactly. So you all get a 15-minute break, and I get a 15-minute break, and we'll move on. We'll make a simple model for detachment. So summary, yeah, this is the one with the most math on it, probably. So summary is, scrape-off layer is narrow, heat flux is large, and we're beginning to understand how we're going to deal with that. I showed you a couple slides back. Actually, I'm going to go back here. I showed you in this slide that if you could get down to sort of 10 eV, boom, you could drop down to nothing, and you got this factor of 300, I claimed, on the heat flux. So, you know, now we were talking something practical. So the challenge is, how do I get down to these very low temperatures? The upstream temperature, according to this calculation, might be, you know, I left, no, actually, this has all the constants. If you put in the real number for kappa naught, then this is sort of 200 eV for the Separatrix temperature in a big fusion system, maybe 300 eV. But we've got to somehow get it down to 10 eV, and then this atomic physics will take care of it for us. So we've got to figure out how to do that. So let's come up with, as it turns out, a pretty simple model that will at least get us an idea of how this varies, of what's involved in this physics. So this is going to be a simple model for detachment, and the goal here is to take away the damn heat. And if I can take away all of Q parallel, then I'm, you know, eventually this thing's just got to go out like a light bulb that you turn the power off on. So my goal here is to get rid of this Q parallel. And you remember this came off the previous slide, and we understand the physics behind that and this pretty strong temperature dependence. So how do we get rid of some of the heat? Well, there is this, if you write down a grad parallel of Q parallel, that's going to be the dropping of the heat flux from one position to the next. That's what a gradient in the parallel direction of the parallel heat flux is. And that's due to volumetrically losing energy. You can think of this is a flux, and so this is the divergence of a flux. And so a divergence of a flux of heat is an energy, a loss of energy, a d by dt of the energy along the field line, dimensionally. So there's got to be some loss of energy that's going to make the Q parallel go down. The Q parallel coming in is bigger than the Q parallel going out, so something in the middle is leaving. And there is this is almost a definition. If I've got some impurities, and this is where the game is going to be played, if I've got some impurities as well as some electrons, the electrons can whack into the impurities. These impurities, say it's neon or nitrogen, this is something whose last ionization potential, as we all know, is 13.6 times z squared. So that's particularly easy to do for neon. If neon were fully ionized, that would be 1.36 kilovolts, right? Multiplied by 100. And so it's going to be hard to get that last electron off. That's the ionization potential. So it's going to be hard to do with 200 eV electrons, a 200 eV temperature. But there'll be some tail electrons that might knock those guys off. There'll certainly be some electrons around that can excite that last electron. That can. So I've got this neon nucleus, and it's got one electron going around in it, or two, or three, whatever. It's got a few electrons going around. Another electron from the free plasma comes by and whacks this guy. This is a slightly classical model. Boom, he whacks this guy. It jumps up to a higher state. This guy who came in leaves with less energy. Really, we do this with a quantum mechanical calculation, right? But basically, this is the physics. Energy is conserved. This guy goes in. He goes out with a lower energy back to the plasma. This guy jumps up to a higher state. He's in some, you know, SPD, whatever state up here, some higher state. He jumps down here. He radiates away that energy. So the energy that had been in the electron cloud went into exciting the nitrogen, the neon, up to a higher excitation state, and then disappeared as a photon. So this is a way of losing energy, is to dump energy from the plasma electrons into the bound electrons, and then those bound electrons radiate. And this LZ is a number you can calculate from atomic physics, and we can basically look it up in tables. And so let me say and clearly it's going to scale with the electron density, the number of guys hitting, the number of guys to be hit, times this LZ. And for simplicity, in effect, I'm going to define an impurity concentration as the number density of the impurity divided by the electron number density. So then I get to do this. And then what I'm interested in is how much CZ do I need? If it turns out that I need, 500% CZ, that's a problem because I can't do that. I can't have, more nitrogens than electrons. In fact, if the nitrogen is significantly ionized, I can't have more than, 20, 30% nitrogen. So there's a limit on CZ. But now here was a clever idea by this guy Lengyel from 1981, and he said, well, we believe this and we believe that, so we ought to believe it if we multiply them times each other. So if I multiply the left-hand side together, I get 1/2 grad parallel of q squared, because this would have been on the outside here, and then q squared, you get a factor of 2. So those two things multiplied together, and these two things multiplied together, so I just took that guy, which is this, and I took that guy, which is that, and I literally just multiplied them together. So this is true. So now then, I'm going to integrate this along the field line, dz. Often people use z as the direction along the field line. And so when I do that integral along the field line, I'm going to get the change in q parallel squared, right? Or 1/2 of the change in q parallel squared. Looks like I put the 2 on the other side. So the delta, the change in q parallel squared, integrating from one end to the other of the field line. And I'm going to want to get down to the detachment temperature. Is this integral dl, well, or dz, I guess I called it, well, grad parallel of te is dte dz. That's what if z is the direction along the field line, some curving thing, whatever. Grad parallel of t. But if I integrate that dl along the field line, I have really dte, because this was dt dl times dl, I've just got dt. So I can actually turn this into an integral dt. And I think I just carried all this gub down here. And so there we are. And now I'm going to take another step, and I'm going to say that I showed you all those pictures that showed that the upstream pressure and the downstream pressure were about equal to each other at temperatures above about 10 eV. So my goal is to get to 10 eV. So I'm going to assume that the pressure is constant along the field line. Because experimentally we see that you can do some theoretical, fairly simple theoretical things and show that you really have to get a lot of loss of momentum from the system to get a pressure gradient. There's not much viscosity, so the pressure is really kind of balanced top to bottom. So I get to assume that the electron temperature and the electron density, that multiple, the pressure, is a constant. So I get to pull out the NE squared, and I can pull out a TE squared from here. And so I get to pull this out, and nicely the densities came out, and all that's left is this integral. And I could take kappa naught out if I wanted to, and I can take, and it's a little bit of a jump. I'm going to say, just to get an idea of the kinds of impurity concentrations I want or I need, I'm going to pull this CZ out of this integral. Well, probably CZ, the impurity concentration, has some spatial dependence, but I'm trying to get an idea of roughly what's needed and how it scales. So I'm going to pull the CZ out also. And so I have a fairly simple integral I can do from the detachment temperature to the separatrix temperature. And I showed you how I got the separatrix temperature. I want to go from the detachment temperature to the separatrix temperature, and that'll tell me how much Q parallel I can take away. So that, it turns out, I can just do that integral. I get the LZ out of the tables, and I do the integral. And what I find is that that integral varies well, let's see, I'm taking the square root of the integral on the other side, of the thing on the other side, and I've got a TE that came from the NE TE. Remember the n squared T squared that I had on the outside. So I got 1t from that. Turns out I get a t to the 1/2 roughly from that integral. And I can just like do that integral. So I've got the Q parallel in gigawatts per meter squared that I can get rid of, normalized by the separatrix density, and I ended up taking the square root of CZ. So what I'm figuring out from that previous slide is that Q parallel can be detached, goes like n separatrix, square root of CZ, t separatrix to the 3/2. So let's go backwards. So if I want this to be the full power, then let's take the square root of this and call that the original Q parallel. So I'm going to take the square root. This is going to be the original Q parallel. I'm going to get a single density, a single temperature, and I'm telling you for all different kinds of impurities, roughly this integral ends up being like a t to the 1/2. So there it is, t to the 3/2. So I now have, this is an atomic database that has been kept up to date. It's pretty good. I now have a dependence, which depends on what impurity, by the way. Argon is a pretty good radiator, but a problem with argon is that it's so high Z that it's not even ionized inside the main plasma. And now it's going to be doing that excitation radiation game inside the main plasma. It's going to short circuit my magnetic confinement. So this is no fun. I don't want to be sticking too much argon into the system. So people think about neon and nitrogen here. Carbon, many machines have carbon limiters, carbon front surfaces, because carbon is very robust. And as we come to my talk tomorrow, I'll talk about lithium, which is less efficient, but it's very low Z. It doesn't radiate from the core. And it turns out to be way more controllable than all these other things. Okay, and I'll talk about that tomorrow. Anyway, so here we are with a TE to the 3/2 dependence. So here it is. So the Q parallel that I can detach and it turns out it doesn't much depend on the detachment temperature. This integral, if you go down to 10 eV and below, it doesn't change too much. So you can just ignore that this end, just go up here. It turns out that Q parallel detachment goes like the density times, putting this all together, the separatrix temperature to the 3/2, and you notice the square root around the CZ. So there we are. We've got that's how much Q parallel I can detach. And it depends again on the upstream separatrix temperature. Now then, let us assume a collisional electron thermal diffusivity, and we'll get to this in a minute, empirical Greenwall density limit. So if we assume this collisional chi-e parallel, from a couple slides back, we had some constants, some kappa naughts and 2/7, and I guess 7/2 inside here, with 7/2 with a kappa naught. So here's TE, looks like this. And here's our old friend, the parallel connection length. So remember, it gets enhanced by the BT over BP. This is the poloidal distance, but the real length gets enhanced because the field line mainly goes in the toroidal direction. And this is a little fudge factor. What this is about is to get diverters to work better. People are talking about taking those magnetic field lines that came down to the diverter and stretching them out, giving yourself more room, more distance along those field lines to do this work. And we'll get a quantitative understanding of the advantages of that by saying this is sort of the extra bit you got. I'm going to say that L parallel is the standard stuff, and then if you were tricky, this is the trickiness factor. I made that field line quite a bit longer. So now then, that gives me some of the pieces I need. I think I've got everything I need for TE sep to go into this equation. But I'm also interested in NE sep and at the separatrix, at the X point. And what we know empirically, and actually I'll talk a little bit about this in a moment, but what we know empirically from lots of experiments is that the density you can get to in these plasmas goes up with the plasma current divided by the cross-sectional area, and actually pi a squared. You might have thought pi ab. But empirically, this is fairly well, there's some scatter, but this is fairly well reproducible over a very wide range. So what we're going to assume is that the density I can get right at the edge can't be bigger than the average density. And so it's going to have to sort of vary with the average density, and I'm going to say this is its factor compared to the maximum that you could get to on average. So, you know, you're going to be lucky if this gets to 0.4 or 0.5, because the edge is going to obviously be less than the average, because particles are leaving from the edge. Okay, so yeah, let's take the a squared over here. We're just looking for proportionality, so we'll kiss pi goodbye. As Ellen Zweibel said, we'll set pi to 1. And now IP, we'll say, is something like, scales like, we're throwing away a mu naught, setting mu naught to 1, which takes some doing, is the colloidal field times the minor radius. But if I want the real circumference, and I do want to keep the scaling factors, I've got a 1 plus kappa squared to the 1/2 to be the colloidal field times the length, which is going to scale like IP. So there we are. I could have canceled that, but here it's all stated out. So now we've got all the pieces we need to plug into Lengel's formula. And while I'm at it, I'm going to multiply it by R naught, because that'll be convenient later. So Q parallel R naught, Q parallel times R naught has an R naught here. And I wanted the density. So here's this density over here. And I took the daring step, I think, of dividing A out of the top and the bottom there. So I have R naught over A and BP. And again, this A showed up in the denominator. And here's this guy. So that's the density. And then, let's see. This is supposed to be the temperature, which is this. And so I've got a Q parallel here to the, I've got a temperature to the 3/2. So I've got this thing to the 3/2 is 3/7. Bizarrely, it turns out all these sevenths and stuff are going to go away when we get done, but let's keep with them. So I've got this Q parallel times L parallel, Q parallel that I can detach times R naught, because L parallel, let's see, what happened? How did I end up with this R naught? Oh, because I took the daring move of putting an R naught here and there, because I was interested, I'm going to be interested in a Q parallel R naught. So here we are. And then I need this L parallel, which is this gub. And here it is over there. And there's the A. And then this R naught just came with that guy for free. BT over BP, L parallel star, my little cheat factor. How much extra longer is it? And again, it's to the 3/7 because this was to the 3/2. And this thing was the 2/7. And this, so it looks like I haven't yet cheated. I haven't swindled you yet. So here we are. And so now I can go ahead and evaluate CZ. I just take all this gub and I put it in the denominator, and I square it. Now, notice that I've got a Q parallel R naught to the 3/7. And so when I divide this thing into that thing, I'm going to get 4/7 left over, but I'm going to square it. So I've got 8/7. And let's see if we can keep me honest. I took care of this. All of this stuff is the same as all of that stuff. And I squared it, so it's the 6/7. And this R naught over A I squared, so there we are. And there's a BP squared. And this lost its half. And there's F Greenwall, and I squared it. So I haven't lied to you yet. So there's CZ. That's how it varies. So one of the things that's a little sobering here right away is none of this stuff has a size scaling to it. You didn't see any net R's. And Q parallel is going to go down as R goes up. But, what did I want to say there? No, let's not say that. Here we've got a Q parallel times R. And it's to the 8/7. So CZ goes like this. I haven't cheated yet. I was going to maybe make a claim that I couldn't defend. So let's stick with this. So now then, I want to evaluate, let's go back here. So I need to evaluate this. All this stuff I know. What was my colloidal magnetic field? What was my major radius? How much should I add to L parallel star? What was my kappa? I can answer all those questions. This one is a little fuzzy. How well did I do on getting the density up at the edge? But these are things I know about my experiment. But this I don't know a priori. R naught I know a priori. I don't know Q parallel a priori. Well, I can get that by using this thin scrape-off layer, this heuristic drift model lambda Q. By knowing how narrow the scrape-off width was, I can figure out what was the parallel heat flux. because it had to come through that thin scrape-off layer. And now I won't drag you through all of this. And here comes the place where I'm not going to carry you through all the arithmetic. This is, slightly subtly, you want to know this lambda q. And I told you that it turned out to be the poloidal gyro radius, and that it's scaled right, and that it just really, all different ways. We've done all kinds of stuff, and it really looks like the poloidal gyro radius, the gyro radius in the poloidal magnetic field. But what I didn't tell you, because the poloidal gyro radius has a TE in it, I didn't tell you what, well, the square root of TE in it. I didn't tell you where I got my square root of TE. So, like, what was that? He says it's the poloidal gyro radius, but he doesn't necessarily know TE at the edge. Was he just lying and cheating? Well, it would come naturally to me. But I used this. I used this. I knew TE goes like that, and I know L parallel. And I have to substitute this back in, because Q parallel is going to depend on the Q parallel is going to depend on the scrape-off width. So I have an algebraic equation that has the TE separatives to the 1/2, right? Because it's the V in the gyro radius. So I've got the 1/7 power. So it's, you know, not a huge effect, but it comes in. And it means that, that if you make a narrower scrape-off width, the temperature is going to go up because Q parallel is going to go up. And so, you know, then you have to go back out again to solve the algebra. And interestingly, the 1/7 turns into a, where's the power? Q parallel is going to naturally go like the power, but there's a 1/8 term that comes from the fact that higher power gives you a higher temperature, gives you a little larger poloidal gyro radius. So that's where some of these 1/8 powers and stuff come from, minus 1/16. All this stuff comes from solving self-consistently the equation, saying that it's the poloidal gyro radius is giving rise to the Q parallel, but the Q parallel is giving rise to the TE, and we can have a lot of fun with algebra, but all it is algebra. And so this is how Q parallel R naught varies. If you believe this HD model, and again, it's not worth going through the arithmetic, but what you get is that this Q parallel R naught, when you plug it in, let's see, is it just the same numerator and denominator? Yeah, did I? Yeah, no, I think I may have changed some things. So this CZ ends up with this mess when you plug all this stuff in, and sort of some cute things happen. Here's a BP to the 6/7 and a BP to the 13/7, and so I just got a plain old BP out of it. And here's a BT to the 6/7 and a BT to the 6/7, and that just disappears. And here's a wild one. I've got 1 plus kappa squared to the 15/14. Like, what the hell? But then I've got a kappa squared to the same thing, the square root of that to the 6/7, so that's 3/7. So that's 6/14. So I have 21/14, so it comes down to a really nice, simple 3/2. And some of this other stuff isn't so exciting. So I sort of justified this step to that step, but from this step, from the other page to this is just a bunch of algebra. But the answer is, oh my God, no size scaling. So the impurity concentration seems to go up with the Separatrix power divided by the poloidal magnetic field and this extra L parallel star. You win linearly. So if you can make that field line length twice longer, then you get half as much impurity concentration. So there is a big win here. And there's a big win here if you can go to twice higher magnetic field. But here we have an idea of how we project the scales from a fairly simple calculation, and only one step where I just refused to do the algebra for you. So you could, if you feel like it, I believe it's true that if you take this and the equation from the previous page, you can derive that. And then but this is real simple. This just pops out, and it's a very, very simple scaling. And the question is this true? And up until recently, people had not got the idea that what we needed to do was kind of do lay of the land studies. It's what we call, we had a big meeting. We have these meetings every 6 months for people who talk about the scrape-off layer. And one of the things we came up with is we really need to figure out what is empirically this scaling. say, if you double the power, do you need twice the impurities? If you, or is it if you double the power, you need only the square root of 2 more impurities? Or if you raise the magnetic field, does that help at all? What about the toroidal magnetic field? Anybody in his right mind would think there'd be a dependence on the toroidal magnetic field because that makes it a longer distance over which you can radiate. But you do it self-consistently and carefully, and it turns out it cancels out. The L parallel star is still there, but the toroidal field part just disappeared. So, what about that? Kappa squared is harder. We don't have very, very big variations in kappa in our experiments. And we don't have too much variation in the Z over A. That's kind of built into the problem. That's kind of most of nature. The charge state divided by the atomic mass is kind of, a half. But what about this, what about that, and what about this? In particular, though, these two are things we could vary. So let's do a little data mining. Let's see if this is what's happening. So right after the paper came out that did that derivation, and I would be far embarrassed to name who did that, they found that the radiated power in the experiments, and it's not that they got my name wrong, it's not that they thought I was Nick Goldston instead of Rob Goldston, this is nitrogen, Goldston. But anyway, the radiated power that they needed to get down to very low temperatures at the target seemed to be pretty much going like that result. Now it's partly that you could scale this result from results from the same machine, from ASDEX. This was this ASDEX upgrade machine. But it's pretty impressive. The F Greenwall at the Separatrix, the fraction at the Separatrix varied by sort of a factor of 3, and the plasma current that comes into the poloidal field linearly varied by a factor of 2, and all this stuff lined up. And there was a different way of doing these measurements, a spectroscopic technique. This was a technique based on the amount of gas being puffed in, and the spectroscopic technique also seemed pretty good to get the diverter temperature down to less than 5 eV. And so these are two very recent papers. So this stuff is now the hot topic, is how does this detachment scale? And I'm sure everybody's looking for ways to break this obnoxious guy's scaling law. And they should be. I mean, that's what science is about, right? Let's break the science. And I encourage that. And here's data from JET. And this is the same guy, Henderson, doing this method of, this is the Joint European Torus in Cullum, doing this spectroscopic method. Now this was a shitty experiment. And I'm not quite sure why he did this, but he's doing it when there's no impurities. The target temperature was only 7 eV. And actually the power they were putting in was only 2.5 megawatts into this gigantic machine. ASDEX, they put in 15 megawatts into a machine half the size. So this is, it was barely attached to begin with. And if you start in a condition where you're barely attached, I had to assume you were above 10 eV even to get started. So it's not that study is not completely legit, but it was kind of in the right ballpark. They didn't have a measurement of F Greenwall Separatrix either, so that didn't help. But roughly speaking, it's detaching with sort of what I had predicted, and as it detaches, the point where the plasma goes out, where the light from the plasma disappears, moves about 6 or 7 centimeters back away from the target plate. Moves up away from the target plate. So that's this detachment. That's where the end of the plasma is, right? It's like 6 centimeters away from the target. That's what you came for. But it's really too easy a problem. And here is some fun data. So this is data from the group in San Diego, from the D3D experiment, that was published long before my paper on the scaling of the impurities came out. So there's a little competition amongst Americans, as I imagine there might be amongst Europeans. So they're a little outraged that it turned out to agree with my scaling. So I turned this upside down. This was an experiment where they did not puff in impurities, but rather they had a background carbon. Their plasma placing components are made out of carbon. And so they had a pretty much constant carbon density. So if you assume this is more or less constant, and this L parallel star is more or less constant, and so on. You can invert that previous equation for the separatrix density. Now it's the absolute separatrix density, not the Greenwall fraction. But you can just take that equation, turn it inside out, and get how the separatrix density should scale. So let's look at this. With the power scan, as they raise the power, this is similar to the picture that I showed you before that had the stuff falling off the cliff. Roughly speaking, you can see for a factor of 4 in power, there's kind of maybe a little less than a factor of 2 variation from the starting point where this thing is falling off a cliff to the at the higher power, but it's maybe something like the power to the 1/2, and that's what you get for n separatrix. Remember, there was a p solid that went with an n squared, so there's a p to the 1/2 that goes with an n. And with the toroidal field, for some reason in their paper, they really wanted the toroidal field to matter. You know, it's a longer length along that field line. It's got to matter. Well, if you just close your eyes a little bit and squint, these lines are really all on top of each other. I mean, it takes a magician to think that there's this much variation. That's what the dotted lines were supposed to say. I mean, it's just not in the data. If you look at that data and you squint a little bit so it's fuzzy, those lines are just on top of each other. So, and you look for the toroidal field scaling, and there isn't any. There's this L parallel star, but that's the sort of extra geometrical factor, and they weren't fiddling with that. So this is pretty close to no variation with the magnetic field. And their poloidal field scan, for some reason 600 kiloamps was the same as 900, but sort of for a factor of 2 variation in the, from the 600 to the 1.3 megamps, it's kind of square rootish again. Maybe a little weaker than square rootish, but there it is, poloidal field scaled, and it's sort of in the right ballpark. At least it shows the right trends as to what matters. So there's and we don't really know how the impurity concentration varied. But this is the kind of thing that's giving us some reasonable confidence that this is generally the picture. There's a lot more work to be done on this. And there's other, well, actually, this is sort of, there's another model I worked with this fellow, Matt Renke, wrote a separate paper. We both came to similar conclusions, a little bit down different paths. But this is a sort of a standing now theoretical prediction. Okay, so detachment is desirable, but it's a little difficult because of that scrape-off width. It's less obvious from the way I did it, but it comes from the fact that the scrape-off width doesn't scale with the system size. That this detachment is challenging. If it were big, if it were 5 times wider scrape-off width, it would take 5 times less impurities. And now then, remember this all depended on the upstream density. And so what's the physics going on in the upstream density? And it turns out that this is limited, again, because the scrape-off width doesn't scale with the system size. So you see a theme here. This is sort of runs through a complete revolution in our understanding of what's going on at the plasma edge. This heuristic drift scaling implies that the pressure gradient at the separatrix rises when the density goes up and the poloidal field goes down. So why do I say that? Clearly, if the temperature is set by Spitzer conductivity, by that thermal conduction model that we talked about, that temperature is going to depend on Q parallel, and it's going to depend on the poloidal gyro radius, because that's how wide the heat flux is going through, and the L parallel. But none of that has a density in it. There's no density in those equations. Remember, the number of carriers and the things you're colliding with kind of canceled in the heat flux equation. So the temperature gradient is kind of fixed. So if I raise the density, then the pressure is going to go up because the temperature was fixed. So the pressure at the edge is going to scale with the density. It's going to vary. If I double the density, I'm going to double the pressure. Then the other thing is that because it's the poloidal gyro radius, as the magnetic field goes up, as the poloidal field goes up, then remember it's QB over m is the gyro frequency, and so the gyro radius is v divided by QB over m. So there's a b in the denominator, and so the gradient, grad p, is going to get narrower, grad P is going to get larger because the density gradient, the pressure gradient is going to get sharper because the particles are only filling up a region that is scaling like the poloidal gyro radius. So this physical result implies that this guy is going to get nastier, is going to get more pressure gradient, more likely to drive instabilities as the pressure goes up. And suffice it to say, without the algebra, that the HD model gives a lambda q value in scaling that's more or less like 1 over the poloidal field. There's some t to the 1/2 stuff in there, of course, that t to the 1/2 ends up varying very slowly with everything else, like p to the 1/8. So if you now assume that the pressure gradient scales like the actual pressure divided by lambda q, which is reasonable because, beyond lambda q, there isn't much plasma, but, you should prove it. That's now supported by measurements from SDX Upgrade. A lot of really good work done by the SDX Upgrade team, and particularly this fellow Thomas Eich there. So let me skip to that and come back. So here is the pressure gradient scale length divided by this lambda q, the heat flux scale length. And there's some scatter, but it's fairly constant. And it's about a factor of 2. I did an earlier theoretical paper where I assumed these were equal, which was, as it turns out, off by sort of a factor of 2. But now this is generally supported by these ASDEX upgrade measurements. Now then, the MHD ballooning limit at the separatrix is given by this. So what do I mean by the MHD ballooning limit? So I told you before that we have a pretty good understanding of sort of the stability, the pressure, the maximum pressure that you can hold in a plasma. And that comes from sort of macroscopic motion of the plasma. It sort of wants to throw itself against the walls. And so we understand that actually at a microscopic level too. And right in the scrape-off width, but actually we've even seen this in the core of the plasma, if you have too strong of a pressure gradient, that wants to push the plasma out. The pressure gradient wants to push the plasma outwards. Now, it's a centrifugal force. So if you think of the field lines on the outside of the donut, I'm in the middle, there's the outside of the donut. On the outside, this centrifugal force, the fact that there's guys flying this way and flying that way, so they really want to go outwards from their centrifugal force, on the outside of the donut, this thing wants to just fly out, but away from the plasma. But on the inside of the donut, I backed up to the inside of the donut here. Now we're on the inside of the donut, and the field lines are still coming around, tilting around. I guess if you think about it, they're coming. Are they going? Anyway, I guess they're going from left to right now. So they're doing this. But they also have a centrifugal force that wants to go out in major radius. They're flying this way and flying that way. They want to go that way from the centrifugal force. That's into the plasma. So the outside and the inside are fighting each other. The outside is unstable. The stuff gets to expand into a lower magnetic field. It just wants to scream out. The inside is actually quite stable because the centrifugal force is trying to push up the pressure gradient. And good luck with that. That's going to be a very stable thing. It's like trying to push a rock up a hill. You're not going to get there. Pushing a rock down a hill is easier, right? But these two field lines are connected to each other. The field line on the outside is connected to the field line on the inside, and so it's a matter of a competition between them as to whether you can get an instability. And the way it works is that if that connection length is large, if you've got a long distance along this field line, it can actually work its way out. It can balloon outwards and bend the magnetic field. So now it's a matter of the magnetic field strength compared to the pressure. So beta is going to come in. It can push the outside out independent of leaving the inside not moving, because the inside wants to stabilize stuff. But I've left the inside stable. I bent the magnetic field, and I've been able to balloon outwards. I've been able to, if you blow on a balloon, it opens outwards. Probably not true that the inside part of the balloon doesn't rise outwards. Maybe it's a weird thing to call it a ballooning mode, but that's what it's called. And it depends on the pressure gradient, normalized to the poloidal magnetic field, because that's what you're trying to bend, trying to bend that colloidal magnetic field. And here what we have is this connection length. There's an A over R here, but this is that connection length. There's actually a colloidal field here that's tied to that. So this, what it's saying is that if you have a very long connection length and a very high beta, then you can blow this thing to smithereens. So, as it turns out, this goddamn Goldston scaling causes this problem at the edge of the plasma. Just this happens because lambda got so short that beta prime got big. D beta dr got to be very big. And so that's what's on the next slide, if I can find my clicker. Oh, here it is. So here, what we found experimentally is that this is this MHD alpha parameter, this is this guy, evaluated experimentally by measuring the pressure gradient versus the Separatrix density compared to the Greenwall density, so that is this F Greenwalled, that we'd like to be very high. What happens is that when you get above about 0.4, 0.45 here, it just stops growing and confinement goes to hell. This is a measure of the energy confinement. It gets, and we have some new measurements that it gets very turbulent at the edge. It's doing this ballooning, and it's just letting particles out. It's refusing to go up in density, and it's just blowing out the heat. And so this narrow scrape-off layer got us one last time. It said that you couldn't go up too high in this F Greenwald. So the edge pressure gradient reached this ballooning criticality at this number about 0.4 or 0.5. And you're very unlikely to be able to go much above that. So, I think we're actually, we have time for lots of questions. Oh no, we're not so far ahead of schedule. So a solution may be coming into focus from all of this. It's really been a revolution over the last 8-10 years, and we'll see how it all totally sorts out. The scrape-off width seems to scale with this colloidal gyro radius, not with the system size. And as a result, the heat flux will be high, and we're really going to need detachment as we move into the future. ITER needs to be, this thing we're building in France, is going to need modest levels of detachment, not sort of full up factor of 300 kind of detachment, but it's going to need some detachment. And so that's an area of active research. But meanwhile, a simple analysis for detachment gives us a scaling where it's, here it is, and now I've highlighted 3 different things we have more control over. This needs more experimental work. I mean, I really just showed you results from mining old data, not so much from experiments that were designed to study this. So, for example, I've been talking to the guys working on JET and ASDEX, which are 2 machines, a factor of 2 different in size. And so we really need to see whether for the same power, the same colloidal field, and so forth, we need the same impurity concentration. Is it true that there's no size scaling in this? Maybe there obviously could be things wrong with this simplified analysis. We've done some experiments with increasing the length, and it does seem to be a win to increase the length. But is that all? Is this the scaling with length? There's more to be done. But a fairly robust, simple analysis gives you this kind of scaling, and we need to compare it to experiments. And so this points, I think, to something that probably makes sense anyway, in that our reactor concepts have been sort of by default at a gigawatt electric, and that's sort of what reasonable size fission power plants are. But if you go to a smaller machine and therefore lower P-sep, plenty of P-fusion, by the way, you want plenty of P-fusion compared to the heating power, you want still very high gain. And so that means if you're smaller in size, you want to be higher in field because that confines the orbits better. And you probably want, so you want lower power per unit size, you want smaller systems, so that's a good thing. You want higher field, and you may want to go for some of this L parallel star, because that's a direct linear win. You really, and some people think even more. So you probably want to do that. And it may be that the advances in high temperature superconductors will allow us to go to higher fields. And this is still tricky. Superconductors, high temperature superconductors can get to amazing magnetic fields, 20 Tesla kind of things, 4 times higher. Well, 4 times higher than ITER, but in a straight cylinder. And there are tricky issues about handling forces, handling fields that come through the superconductor at funny angles, so and also handling the quenching of high temperature superconductors. When they go normal, it's hard to detect because they started pretty high temperature in effect. But if we can get this to work, then that points to the possibility of making smaller systems, therefore lowering PSEP and raising BP. And maybe we use them to create some space for more L parallel. And it looks like a solution. It's going to take some creativity. It's going to take a little changing of direction because of this physics that's become clear in the last, well, this stuff is just a few years old of trying to get this kind of scaling or come up with a scaling. So this is only a few years old, and so it may take some rethinking a bit about how we want to make a fusion reactor, but I think it's actually a good direction. I think smaller size, lower power is probably a good direction for any energy source these days. So, lots of time for questions. Thank you very much. It's late, but you're welcome. You're very welcome to ask questions. Throw fruit. That's what usually happens to me at a scientific conference. Go ahead, Tim.
Short one, the smaller size refers to the machine, not the type of equipment.
Yes. Well, actually, this L parallel star is, yes and no. So yes, it's a smaller machine. This L parallel star, remember, is just a fudge factor for for changing the shape. So you could if you keep this constant, that means the diverter size stays the same relative to the system, so the diverter actually got smaller. And you still win by a lower PSEP and a higher magnetic field, higher BP. But I think you're probably going to want to use a little more vacuum vessel space to extend the field lines here. One way you can do it that's interesting is that, and this takes a little tricky design, but actually, why don't I go back? Go back a bunch of slides. So maybe I'll go back this way. So, the fact that these field lines are coming together here means that the poloidal magnetic field is getting stronger. These are lines that separate a certain amount of poloidal magnetic flux. So where this is wider, the field is lower because I've got a certain amount of flux that I've got inside of here. So and so on. And so where they're narrower, that means that the field is higher. Flux is a 2 pi r times the distance here, times the magnetic field. So this distance being smaller means the magnetic field is higher. So what you can do, if you're tricky, is to not make the diverter with a single coil here, but do some of the work with another coil over here someplace. So these 2 coils are doing the work to pull the field lines this way. Between them, they have fields that go around this way, go around them this way, so it pulls it out a little bit more. So it's going to be coming out a little bit more. But then, if this thing is trying to go right through between these 2, the field there, the poloidal field there is 0, because these are both facing the same direction. They're both currents that are in the same direction as the main current. So this one's field is this way, this guy's field is that way, so they're fighting. And so as this goes into the space between these 2, it's spreading out. The poloidal field is getting smaller. So what's exciting about that? Well, what's exciting about that is that if the poloidal field is smaller, that means to get that poloidal distance, I have to go more around the torus, because BT over BP is higher if BP got smaller. So it's moving slowly this way, but the same speed this way, so L parallel gets larger without making the vessel a lot larger. Now it's a little complicated. Those coils are opposite. These coils here are making magnetic fields that are crossing the main field the main coils that are making the big field, and so it's torquing that coil pretty good. So there's some forces that have to be studied, and there are people. Actually, the European team has done a very good job of beginning to quantify the challenges with that and their advantages. But that's a way you can play with L parallel, an L parallel star, therefore. So, are we up? Good.
So with ether, we want to operate on a semi-detachment.
Right.
Semi-detachment. So
I think the semi is getting a little as we keep studying through this, it's looking more like we better get it pretty well detached. But yes.
Okay. No, because yeah, we talked about detachment is we did detachment and blah blah blah. But what are the downsides? Like
What's the downside of detachment?
yeah, why did we say we want to operate in semi-detachment, or why not go full detachment every time?
Well, because as you saw, it takes some CZ to get detachment, and that's impurities, and impurities don't fuse. And if say I had a few percent of nitrogen in the plasma, then that's going to take away, whatever 5% of the. It's going to use up. Let's see how to say this. It's going to use up the electrical space for, depending how ionized it is, 5 or 6 electrons, 5 or 6 protons or deuterons or tritons. So if I dilute the ions, because I need charge neutrality, I'm going to absolutely have as many electrons as Z times the ions. Because if it's not almost exactly balanced, there's an insane electric field, which will suck in the electrons as needed, or expel the electrons depending on its direction. So I'm going to have just about charge balance, and so using up the beta limit on electrons that don't fuse and on impurity ions that don't fuse, but I've got a fixed beta limit, is a problem. And that's
Is that the only reason?
another reason. So there's some. Okay, we can go through them. So another reason is that lowers the power because the beta limit is somewhat fixed. It also means that the fusion power that you're making for a given energy in the plasma is lower because the energy came down some, but the fusion power goes like n squared. So the fusion power went down more than the energy went down, and so that triple product, that NT tau, got worse and the gain got worse. So now I wanted 10 times more power out than I put in, and now I'm going to get like 6 times more. And so that's not very satisfactory, if I don't have as many D's and T's colliding with each other as I had wanted. So that's also the issue of depletion. There's also an issue. Go down the whole story. There's also an issue that if you go with higher Z impurities that radiate from the core, you're going to lose energy that was supposed to be confined and only leaking out by turbulence, but now it's also leaking out by radiation from the core. So that's not so nice. And there's Bremsstrahlung right in the middle. As you raise the Z of the plasma, electrons are zooming past these charged particles and scattering. And so they're changing their velocity, they're accelerating, and so they're radiating. So it's called Bremsstrahlung radiation, stopping radiation, but it's really acceleration radiation or deceleration radiation, if you like. And that goes like Z effective, like the Z squared of the ion. So that's another problem. You don't want to do too much of that. And then another problem, but I'll get to a good piece of good news in a minute. Another problem is that right at the diverter target, electrons are screaming into this diverter target, but they can't keep screaming in there forever because the ions are moving much slower. The ions are moving into the diverter target at sort of their thermal velocity. The electrons are screaming in at their thermal velocity that's 60 times faster. So you end up with an electric field that retards the electrons, so that the flux of particles along these field lines has got to be equal numbers of electrons or ions, or this charges up to some insane voltage. So it has to be very close to the same number. So that means there has to be a big retarding potential for electrons right at the diverter target. It turns out to be about 3 times the electron temperature. You need to get the number of electrons coming in to be about equal to the ions coming in. So now that will accelerate impurities like mad. Suppose I have a 3 times charged nitrogen ion. That will get accelerated down this potential. It'll be accelerated to 9 TE. And then it will hit the target, And if it isn't fully detached, and so it really gets down there and hits the target with a good high energy, it will sputter away the material the target's made out of by hitting it with these energetic ions. The slight piece of good news is that the turbulence in the core, in some situations, seems to actually be reduced when you have impurity ions in there. It's not something we have a good, solid understanding of, but in some circumstances, and people are doing these advanced computer calculations to really understand, but there are circumstances where the core turbulence is reduced by the presence of the impurities.
The ETG turbulence.
Pardon?
ETG turbulence.
I think it's ITG turbulence that's mostly affected. He's in the know. Okay. Oh, 2 more questions. Great. Vince.
So, if I understand well, stability strongly depends, is defined by the fact that you have less magnetic field outside of the plasma, right? So there is a gradient.
Less magnetic field on this side and more magnetic field on that side.
Yeah.
Mm-hmm.
And I was wondering that, do you really need higher field, or you would be happy with a super homogeneous magnet, which generates the field for you?
You really don't have a choice other than to have a 1/r magnetic field. You're kind of stuck with that because you've got a current conductor right here carrying current, and maybe you've got a clever idea, but at least as far as I understand, you've got a current that flows up here and it comes back around. There's coils that go both ways and come out this way and go the other way. There's a bunch of, you've got a cage of this current. But fundamentally, this is going to make a 1/r field because of Faraday's law. Or Ampere's law, pardon me, Ampere's law. So I don't think there's any, well, there's a whole other world of what are called stellarators that, where you can play games with magnetic field strengths. But in a tokamak, in a system that is toroidally symmetric, you pretty much don't have a choice but to have higher field here and lower field there. There are funny games you can play with twisted magnetic coils, the coils that aren't axisymmetric, that allow you to bend the magnetic fields around here and around here. And you kind of can arrange, at the price of a much more complex geometry, you kind of can arrange a system that is more uniform in a magnetic strength on the 2 sides. You pay for it with with a more complicated geometry, and it has its own set of beta limits that as the pressure comes up, there are currents that are driven in the plasma by the pressure itself, and those tend to sort of scatter the magnetic field lines and make the whole system much more likely to become ergodic at high pressures. But that's another area of research, and the W7X group in, help me? Greifswald is doing nice work on that. Go ahead.
So I was wondering, you mentioned this cliff where if you get to maybe 10 eV, then the plasma by itself goes down to maybe 0.1. So
yeah.
What's actually the background on that? Why does that happen?
Well, there's a bunch of stuff going on there. Let's do this. So if we go down to, where's this picture? Is that it? Nope. There, no, fully. There's a picture. It must be higher. That one. Nope. That one. There we go. So what starts to happen here is that you begin to get some recombination. And also another thing that happens here is that you get some charge exchange where the ions that are in the plasma can collide with neutral atoms that are outside of the plasma that come in and touch the plasma, and they can exchange energy with those, and so you now, or exchange electrons with those really. So you now have a neutral hydrogen that's very energetic and a charged hydrogen that's not so energetic, and so that cools the ions in the plasma. You can also have and also takes away momentum from the plasma. You can also have collisions between the plasma pluses and the deuterons that take away momentum. And what that does is lower the pressure of the plasma, because it's the pressure pushing against whatever momentum sinks there are. And so if there's a big momentum sink, then the pressure drops, the grad P balances with the momentum loss. And so these two processes accelerate the motion down to lower energies. And then the recombination really takes energy out of the plasma. So there's sort of an accelerating process as you go down here, is in effect what's going on. There's some more stuff that has to do with electric field drifts that also contributes. Let's see. Go back here. So what's to say here? There's a, I told you there's a 3 TE temperature, there's a 3 TE potential drop. There's also field lines on this side. And there's a 3 TE potential drop between the plasma and the target, because that's what holds back the electrons. And so there's a potential difference between here and here, between there and there. And in the usual direction where the grad B drift is downwards, it works out that the magnetic field is such that particles that come in here are pushed by the E cross B drift this way. So there's a radial electric field this way, because of the potential isn't so hot. 3 TE isn't much here, but 3 TE is pretty high there. So there's a potential difference, so there's an electric field difference. And so as it turns out, the the E cross B drift is this way, and it piles particles in over here. And as you get that big, and so that tends to raise the particle density in this region. And as that and then as the temperature drops, the density rises, and all those processes get faster. And so you get more of a falling off a cliff effect when the grad B drift is this way than when it's that way. So that's an additive factor.
Yes.
Oh, sorry. Carlos.
I have two questions. Why are double null configurations not very much used as it was proposed since the origin of MAST?
Mm-hmm.
And do you think that playing with the geometry, in this case of expanding the magnetic surfaces,
Mm-hmm.
or doing the Separatrix, the divertor, or snowflake things, these geometric tricks would help very much to
Well, so why not double nulls? You know, I think you're suggesting that maybe double nulls would be good. So what's a double null diverter, for those who aren't in the know? That's if you can very, very carefully balance it so that this field line is also a separatrix at the top. See, the separatrix is way outside here. In this case, this single null, there's a null here, null in the poloidal field. A single null, if you made this field line really be the same as that one, you could make a double null. So there's a problem with that, which is that it's very hard to get perfect balance. I mean, particularly, there's another case where the narrow scrape-off layer has come to shoot you in the head. So if you have an extremely narrow scrape-off layer and you want to get balanced like the narrow scrape, you've got to be balanced better than the scrape-off layer width, or you didn't really do anything with the double null. Now it's way harder. And it gets harder when you get to a bigger machine, because relatively speaking, the scrape-off width is narrower. So it's very hard to get good balance. So that's one of the reasons. You kind of have to assume that some of the time you're going to be completely unbalanced. So you kind of have to survive the case when you're a single null, even in a double null design, because it's so hard to balance precisely. When we looked at this many years ago for a design Princeton was doing, we decided you just had to assume that 2/3 of the power went to the bottom and 2/3 of the power went to the top, which is, of course, insane. But you just had to assume that because you didn't know, you didn't have perfect control. And so you really were only gaining 1/3, right? So you didn't get a factor of 2 gain, you got a factor of whatever that is, 1.5 gain. So those are some of the things. Factor of 1.5, there's something to be said for that. But then the connection length, it's not completely obvious that the connection length will, since it's due to this grad B drift, and it's at least we think so, and it's localized here, how it will play in a double null is actually not so clear.
And do you think that playing with
Oh.
geometric things are...
Well, I think it's fair to do this study and to try to figure out, because the forces on the coils are a big factor, and the strength of the magnetic field you can get to depends in part on the forces of the coils and the structures you need to react those forces. So, you know, did you make detachment easier, but now you've made it so that the plasma needs to be, or the coils need to be much bigger to get the same confinement and power production. And so, you know, there's a trade-off there. You know, the fact though is that this problem with the power flux to the diverter is what sets the size of these machines and is driving the European groups anyway to very large size machines, which I think may be a little wrong-headed based on what we now know about detachment. So exactly playing that out, it may be that a small high field machine where you do play with this diverter is a wiser approach. Because it's really that L parallel star that comes into the problem, not the size of the machine. Bigger machine doesn't help, just makes PSEP bigger. So you heard a little bit of a radical approach here that is not exactly the completely center of the error bars of what people think. But that's what makes it, to me anyway, fun. You got to challenge accepted wisdom. Okay, well, let's go get something to drink. Oh, it's past 10.